Q1, well, it's in state Q1, and it sees a 0. What does it do? Well, it's in Q1 and sees a 0, it goes over to Q2. Okay? And what does machine M2 do if it's in state P1 and it sees a 0? Well, it stays in P1. Okay? So this is the first transition rule. If you're in this state of M3 and you see a 0, you go to that state of M3. All right, let's just do another one. Well, before I do another one, let me ask, how many transition rules will there be for machine M3? Yeah, 8. Exactly, because we have 4 states, and we have an alphabet size 2. And so it will be 4 times 2, which is 8. So let's just look at what's delta 3. Let's just take the second state here. Q1, P2. Q1, P2. Okay, and so I guess I should have also said what happens when you see a 1 here. We'll look at that in a minute. So we'll look at what happens when there's 0, 1 here. Okay, so what does happen in Q1, P1 when you see a 1? So you go over here and you say, what happens when you see a 1? You stay in Q1. What happens when you see a 1 here? You go to P2. So it's Q1, P2. That would be Q1, P2. All right, and what happens if you're in Q1, P2 and you see a 0? Well, what happens if you're in Q1 and you see a 0, you go to Q2. And when you're at P2, if you're in P2 and you see a 0, it's a P2. So what was that again? What did I just say? It's Q2. Okay, and what? P2, okay. And what happens here? It's what, P1? No, can't be P1. Q1, P1? I don't know, I'm not processing it. Is that right? How many people, we'll do crowdsourcing here. How many people agree with this? How many people disagree with this? Okay, and how many people didn't answer? Okay, and why? Is what? Okay, all right. Okay, but does everybody disagree with this? All right, well, you can check it out at home. Anyway, as long as you get the idea now, you can build the transition function. Okay, and now what's the final state for this machine F3, the final states? Well, we're looking for an OR. Okay, so you use two languages with the OR. So if either of those machines reaches an accept state, then you want to accept. So what are the states from M3 that have the property that one or the other, or perhaps both of these machines, M1 and M2, accept? Well, if you're in the state P1 and either P1 or P2, or you're in P2 and Q2. Okay, so it's Q1 P1 or Q1 P2 or Q2 P1. That's going to be a little crowd over there. Q1 with P1 or Q1 with P2 or Q2 with P1. Those are the 3 states of M3 that are the accept states for the language A, union B. Okay. Well, why are only 3 and not 4? You have to push 4, right? Because it's Q1, and anything from here, that's 2, and P2, anything from there, that's another 2, and that makes 4 altogether, but we only wrote 3. Yeah, because the Q1, P2 came up in both of those cases, all right? And so we only need to write it down once. It's, wherever it was, Q1, P2. Okay, got it.
Final state of that should be Q2, P2.
Q2, P2. Oh, did I write this wrong? Okay. Oh, I see. Yes, I did write that wrong. Thank you. It's a P2 because the P2 is the accept state from M2. Okay. Now, this describes the transition function, describes the final state, the start state, the set of states, the alphabet. So that completely describes a finite state machine. Or a deterministic finite state machine. Its transition rules, everything's there. I could try to draw this as a diagram here or something like this, but it would be kind of messy. And so it's often the best way of describing a finite state machine is just through the listing out of the transition function. I could put the transition function in the table. Also, that's another way of displaying it. But anyway, all the information is there to describe the finite state machine. So why does this work? Why is this the finite state machine that accepts A union B in this particular case? Because what it's really doing, if you feed a string into this finite state machine, what it's doing is it's essentially running both of the machines, M1 and M2, in parallel. It's keeping track of what M1 would be doing as it's processing the string, and what M2 would be doing as it's processing the string. It's doing that by having these 2 states put into one state. The 2 states of M1 and M2 are joined together as a pair to be a single state of M3. And every time that the machine M3 makes a transition, it's really basically saying, what would M1 do? And what would M2 do on that particular character? And just recording it in the pair here that names the state of M3. Okay, so if you get that idea, and then here, the final states, the accept states, are any pair that, any pair of states that has an accept state, either from M1 or M2, or maybe from both. If you get that idea, then it's obvious that this is right. And in fact, the book, I think here at this point, maybe it's in a different one, has a theorem and a proof. It says proof, P-R-O-F, and then it starts telling you something about it, and then it says, it's obvious. So in my mind, it's not a proof. I mean, if you're going to say it's obvious, then that's, you might as well just do it without saying P-R-O-F. But this is obvious once you get the idea of how this works, how this is simulating, how it's really recording what both of those machines, M1 and M2, would be doing. Let's just look through a small example, and hopefully I get it all crystallized. So again, I just erased what this language is. This is a language of strings that have an even number of zeros and an odd number of ones. So it's an OR, so even number of zeros. Let's take that one. Okay. An even number of zeros. Well, not in this lifetime anyway. Not in this universe. Okay. An even number of zeros, but also an even number of ones. So this is in A, right? So it's not in B. But it does mean that it's an A union B. Okay. So this string is an A union B. So if we process this string, let's call this W. So we want to compute, we want a computation of M3, and then we give it W. So what state do we start out in? P1, P1. That's where we start. Okay? And then you see a 0. So what state do we move to? I can tell this example is going to overwhelm me. I'm not good at doing examples on the board. I get tired. But Q1, P1, we actually did figure that one out under 0, is Q2, P1. Q2, P1. That sees a 0. And why? It's because machine M1, if it was in state Q1, that sees a 0, would move to Q2. And machine 2, if it's in P1, that sees a 0, it would go to P1. Okay? So we just simulated the first step of both M1 and M2. That's what M2 is doing. It's simulating what the two different machines would do. And then we see a 1, okay? So if you're in this state, Q2P1, we didn't write that out before, Q2P1, you see a 1. But to figure out what M3 does, what's the rule for M3, is, well, what does M1 do if it's in state Q2 and sees a 1, that's a Q2. And if you're in P1, here, and you see a 1, you're in P2. So Q2P2, right? Q2P2. Okay, that's what sees a 1. And then, we'll go back this way. The next one is a 0. Okay. Those are the entire sum. Everybody get the idea? And we're basically, the M3 is simulating both M1 and M2. And then as time processes this last one here, if you do this one, when you do this at home, you'll crystallize better. You should be in the final state. Yeah, let me just, no. You're going to ultimately be in a state which is accepting for A. And we're going to be accepting state for A is Q1. Okay. If you're not in accepting state for B, so what state would you be in if you're not accepting for B? It would be P1. So this is my claim. If you actually go home and crunch on this and walk through these various rules, on this particular string, you should end up in Q1, P1, and that's an accepting state for M3. Q1, P1. This is the final state or accepting state for M3. Okay. Now, this little example I made up, so it's not in the book. You should just write down what the language is, and then you can do all this reconstruction yourself and check this one out. In fact, maybe I'll make that as a homework. Part of the next homework is to check out this string, show me the actual computations that M3 would do. Okay. So let's now, I have to write that down. I don't want to do that. So 0, 1, 0, 1, 0, 0, 1, 1. Okay, so let me just try to write this down more formally. What it means for to build the device machine that accepts the two languages. So a more formal definition. Page 3. Page 4. Okay. So this is delta for the union. Okay. Sorry. breaking down in more formal mathematical notation what we just did over there on a particular example. And so another way of saying this is that Q3 is equal to Q1 Cartesian product with Q2. That's the Cartesian product. Sigma is the same. Okay. And Q0, that's the start state for Q3, is because even the book is inconsistent about what's the subscript for the start states. If the book had always said every start state is always Q0, subscript is 0, that would be okay, but we're not being consistent here. So I'll just say that the start state of M3 is the pair of start states from M1 and M2. Which again, we saw by example. And then the most important specification is the transition function. The transition function for the machine 3 is R1, R2 under single, say, binary alphabet. Is equal to delta 1 of R1, 0, and what goes in here? Delta 2 of R2 X0. Right? And similarly for 1, or more generally, more abstractly, we could just say X. There's that mysterious X again, where X is some member of the alphabet. Right? So this is just saying, what you do in machine M3 when you see this particular pair is to simulate what the other two machines would do when they see, when in those particular states, and they see that particular character, X. Okay, and then the final state, the set of final states, is R1, R2, such that R1 is contained in F1, or R2 is contained in F2. Okay? So you're simulating, M3 is simulating those two different machines, and we're talking about the union of two languages, which means we'll accept the string if it's accepted either by machine M1 or it's accepted by machine M2. And that's why we have an OR here. If we end up in a state in M3, which has an accept state from F1 or an accept state from F2, then we should accept in M3. That's the OR. Okay, that's the complete formal specification. And on your homework, you have questions, I think it's 1.4 or 1.6, something like that. The questions in that series ask you, they ask you the hands. We'll do the hands in them. Okay. So this is Herndon, and I claim that this is essentially, if you write this down nicely, what we just did, and you throw in some explanation for why this is right, that's a proof. Okay. And in the book, they started to do that, but then they said, okay, that's obvious. I mean, which is essentially right. If you think about this, it will just become obvious that this is correct. How many people find this obvious so far? Okay. Well, if you didn't find obvious, how many people will survive at this point? Okay, good. All right. So the rest of you will get it when you think about the privacy of your own mind. All right. So that shows, that is what I've just been doing is a proof, a demonstration, a constructive demonstration of the fact that if A is regular and B is regular, then the language A union B is regular. It also shows you constructively how you can build a Frank machine that's for the union of two regular languages. Oftentimes, for example, in this case, the two regular languages are both very, very obviously regular. I just say two regular languages are obviously regular. The two languages are obviously regular. There's a simple Frank machine for each one of them, if you need to construct them. But it isn't immediately obvious how you wouldn't just be able to write down necessarily the union of those two. But this proof gives you a procedure, a mechanical procedure for getting the Frank machine that recognizes the union of those two languages. So if you have a homework problem or an exam problem that asks you for the Frank machine that accepts the union of two languages, then you can go through it mechanically if you don't just immediately see how to do it anyway. You can always solve things that your pants if you're good at that. But here is an actual procedure which you can use, or it tells you more generally that the union of two regular languages is regular. Okay, what about the union of three regular languages? If A, B, and C are three regular languages, and now I'm interested in the language which is A, union B, union C. What about that?
Will be regular.
Okay, why?
You can go A, union B, and then another language B is regular, and then it's just union of B.
Exactly right. That's a good way of doing it. And in a sense, what you're doing is a kind of inductive argument. So if A, B, and C are regular, then I was asking about the language A, union B, union C. And what was pointed out is that you can think about it this way. A, union B, we just proved that's a regular language. Okay, so that's now some regular language, we can call it D. And then what we have here is the union C. That's the union of two regular languages, which is proved as regular. So the union of three regular languages is regular. Okay. And if I ask you on the exam whether the union of five regular languages is regular, that should be an easy question now. Okay. All right. Now what about the intersection of two languages? Okay. So we have A and B are regular. Okay. What about A intersect B? Remember, the language is a set of strings. It's a set. There's two sets, so you can do set operations on them. So you can take the intersection. A intersect B. Okay. If I wanted to prove that any language, if whenever A and B are regular, A intersect B is regular, of course, the only tools we have available are the same kinds of things we were just doing. We know there's a finite state machine for A, we know there's a finite state machine for B, and I'm trying to construct, in general, a finite state machine that recognizes A intersect B. Okay. Any suggestions? Right. So what's suggested is you do the same thing. You still want to simulate the machine for A, M1, the machine for B, M2. But now the accept states are different, the final states are different. And what are they? What I mean in this specific example, but yes, that would be what it is in this specific example, but in general, how would you describe it? Yeah.
So every translation that goes to that, my final state?
Yeah. Right, so here, F is going to be F1 plus F2. And essentially, this is an and now. It means you have to be in a final state for the first language A, and you have to be in a final state for the second language B. So the entire construction is exactly the same, except for here, F, you change this or to an and. Okay. And this is what I was saying earlier, the union really corresponds to or conditions, the intersection corresponds to and conditions, and this is where you see that actually taking effect, the difference between or and and. Okay, so the intersection of regular languages is regular. And your homework, 1.4 or 1.6, I don't remember which, asks you to show particular languages or intersections of regular languages to come up with a deterministic finite state machine for those. And again, you can do those by seeing your pants. So it actually asks for also for the finite state machine for each of the individual languages. So you have to do those. But if you then just see how to put them together, just like this, that's fine. Otherwise, you can come up with a deterministic finite state machine for the intersection. And sometimes after you do this mechanical procedure, you can recognize that there's some simplifications as well. The machine doesn't have to have all of those, it doesn't necessarily have to have all the transition rules. Sometimes you can see simplification. Okay, is that clear? Good. Now, nobody said no, so it must be. So now I've finished what I intended to do on the first lecture. Now we can start the second lecture. All right. Well, also one more thing in relation to the homework. So now you have the tools to do about the first half of the questions, and hopefully we'll do enough the rest of the lectures, you can do the rest of them. The very last question in the homework, I think it's 32, something like that, 1.32, asks you about some computation on matrices. All right. So I don't want to be completely specific about this, but like a binary matrix, something like that, and it asks you about doing computations. I think actually it asks you to do the and, to do the sum, sorry, of anyway, my point is that it turns out that in that problem, okay, each one of these columns is a character in the alphabet. So the column of binary numbers is a single character in the appropriate alphabet. So look at the alphabet, so all I want to point out is that the alphabets don't have to look like the English alphabet or the ASCII alphabet. They're just a set of objects. In this case, the objects are columns that come from a binary matrix. Okay? And so when you look at that problem 32 and you're confused, where is the alphabet? What is this machine computing on? Each of the columns is actually an element in the appropriate alphabet. Okay? All right. And that's sort of similar to what was happening over here, that these state names are really a little bit odd. And as I said, if you think like a mathematician, it's okay that names look a little weird, or that elements of the alphabet look a little weird. They're just sets of the appropriate type under the appropriate conditions. Okay. Now, we're going to, the way the book proceeds at this point is to talk about concatenation of two regular languages. First of all, what is concatenation? Of two regular languages. Okay, so A is regular, and B is regular. The concatenation of those is in this way. A circle B is a set of strings x, y, where x is contained in A and y is contained in B. Okay, so let's just take these languages over here again. One was A was the set of strings that had an even number of zeros and B was the set of strings with an odd number of ones. So if I have 0, 0, 1, 1, 0, 0, 1, 0, 1, 0, 1, okay, this string is an A, right? Because it has an even number of zeros. And this string is in B. Okay? So I can think of this string as X followed by Y, where this is X and this is Y. So basically we're saying that a string is accepted, or a string is in the language A.B, if there's some way of breaking up that string into a first part and a second part, where the first part is in A, and the second part is in B. Okay? So let's